Section 10.4, Hypothesis Test for a Population Standard Deviation. In this section, we have one objective. We want to test hypotheses about a population standard deviation. In this section, we discuss methods for testing hypotheses regarding a population variance or standard deviation. Why might we be interested in testing hypotheses regarding the variance or population standard deviation? Many production processes require not only accuracy on average, the mean, but also consistency. Consider a filling machine, such as a coffee machine, that over and underfills cups, but on average fills correctly. Customers are not happy about underfilled cups, and they are dissatisfied with overfilled cups because of spilling. They want a machine that consistently delivers the correct amount. As another example, consider a mutual fund that invests in the stock market. An investor would prefer consistent year-to-year returns near 12%, rather than returns that fluctuate wildly, yet result in a mean return of 12%. Both of these situations illustrate the importance of measuring variability. The main idea is that the standard deviation and the variance are measures of consistency. The less consistent the values of the variable are, the higher the standard deviation of the variable. We begin by reviewing the chi-square distribution. The chi-square distribution states that if a simple random sample of size n is obtained from a normally distributed population with mean mu and a population standard deviation sigma, then we have the following formula. Chi-square is equal to n minus 1. You have s squared over sigma squared. It has a chi-square distribution with n minus 1 degrees of freedom, where s squared is a sample variance. Now remember that the symbol chi-squared is pronounced chi-square. Critical values of the chi-square distribution are in a table in the appendix. Now again, characteristics of the chi-square distribution. Number 1, it is not symmetric. Number 2, the shape of the chi-square distribution depends on the degrees of freedom, just as with the student's t distribution. Number 3, as the number of degrees of freedom increases, the chi-square distribution becomes more nearly symmetric, as illustrated below in figure 20. And number 4, the values of the chi-square are non-negative, greater than or equal to 0. So again, recall from figure 20 the chi-square distributions. You can see that as the degrees of freedom increase, then it becomes more and more a symmetrical figure. Now recall that in the table, it's structured similarly to the table for the t distribution. The left column represents the degrees of freedom, and the top row represents the area under the chi-square distribution to the right of the critical value. We use the notation chi-squared with the subscript alpha to denote the critical value, chi-square value, for which the area under the chi-square distribution to the right of chi-square subscript alpha is alpha. So for example, the area under the chi-square distribution to the right of chi-square with an alpha of 0.10 is 0.10.